Oh, it's not asking me to confirm. That's different. Okay. Interesting. All right, that's different. Different days, different things. We'll see if this works. The other thing that I noticed on there was there are definitely some people in here who have difficulty with long multiplication by hand. Like 17 times 13, I saw a couple people, that not just one or two, but several, who when we had 17 times 13 were doing this. I mean, wrote down 13 17s and adding them up. All right? I mean, 17 times 13, hopefully for most people in here, is a mental math exercise. At the very worst, it's a long multiplication exercise. But just as this is a check, I checked with my 7th grade daughter to see if she could do it in her head on the way into school today, because I was thinking about this. And it took her about a minute, but she was able to come up with 17 times 13 without a calculator or a pencil and paper. 7th grade. Okay? No, she just knows her mental math. I mean, to do 17 times 13 in your head, you do 17 times 10 plus 3. That's how you think of it. And 17 times 10 is 170, and 17 times 3 is pretty easy. That's 30, and 21, that's 51. You're just doing that in your head instead of on paper or on the smartboard. All right? That's one of those skills that's just that's one of those little hidden weaknesses that you might have right now as you're heading into calculus. And that's really kind of one of the jobs of pre-calculus, is to kind of sort out where you figure out, so you can, not for me to figure out where you have weaknesses, but for you to be able to figure out where you still have weaknesses in math. Because you want to get those sorted out before you hit calculus or college math. You don't want to be walking into a college math class and not being able to do multiplication like that, because it gets bigger and nastier when you get into college. And not every college class allows you to use calculators. Now, it depends on where you go to college. I know that at least up until a couple of years ago, UW-Madison, for most introductory math classes, did not allow any calculator. Most calculus and differential equations classes, no calculators ever on tests. Not at all. In fact, I was talking to Sarah Lomborg, who graduated from here, 5-6 years ago, and is a math teacher over at Parker now. I ran into her yesterday. I was asking her about that. She wasn't hurt, don't worry, when I ran into her. Little joke. No. But, so yeah, that's, it's just one of those things, learning how to do that mental math. So if that is an area of weakness for you, ask about long multiplication. I mean, if you have to do it 17 times 13, just the old multiplication way, or just 3 times 7 is 21. Carry the 2. 3 times 1 is 3, plus 2 is 5. 1 time, you put a 0. 1 times 7 is 7. 1 times 7 is 1. It's exactly the same thing we did here. Same numbers, 170 and 51, just a different way of doing it. 1, 2, 2. Okay? But those processes of long multiplication and stuff like that, and long division for that matter, those are processes that are important. And you can't always just rely on your calculator for that. Some of you have just become, I'm sure you know how to do it, but you've just become a little over-dependent on the calculator. And it's just one of those things that, oh yeah, maybe I do need to think about that. I mean, the people who did the multiple addition thing, they got the 221. It's just really, you went through all that. That's not where you want to be. Okay, I know you can find the answer. The question is, can you find it efficiently? And I want you to be able to find it efficiently. So, people did mostly better with sine, cosine, tangent thing as far as identity angles. There are still some people who are struggling with values of sine, cosine, tangent, and identity angles. A lot of people really struggle with sine and cosine of 270. which is sine of 270 is 0, and I'm sorry, cosine of 270 is 0, sine of 270 is -1. And a lot of people struggled with that one on the test. So again, knowing the values of sine and cosine at identity angles are still going to be, there's still going to be a premium on that because we aren't really switching off from this whole idea. Now today's lesson is pretty much almost completely unnecessary in many ways, because it's very much a review of what we've done before. It's the double angle identities. And we've actually already done these. We've proven these identities in the homework. This is strictly review at this point. Although we've never formally presented them before, you have seen them. You've actually, like I say, you've actually derived them as part of your homework. So sine of 2x, cosine of 2x, and tangent of 2x. Remember doing these proofs in the homework? These are proofs you did in the homework. So sine of 2x is simply sine of x plus x, which is sine x cos x plus cos x sine x. But cos x sine x is, of course, the same as sine x cos x. I guess I'm not as oriented as I thought I was. So sine x cos x plus sine x cos x is 2 sine x cos x. Now again, these are identities that you can memorize or you can choose not to memorize. It's really up to you, because we don't have to use them necessarily. But they are handy to have kind of in our hip pocket. But we can always, if you don't have them completely memorized, if you at least have the basic sine alpha plus beta from last week memorized, and cosine alpha plus beta, you can figure these out very quickly. So you don't have to necessarily totally memorize these, because you can always derive them very easily. Cosine of 2 alpha or 2x, same thing. That's a cosine of x plus x, which is cos x cos x minus sin x sin x, or cos squared x minus sine squared x. Now, this is one that we often mess with using our Pythagorean identity. And we re-express this one several different ways. Because sine squared x plus cos squared x equals 1, I can re-substitute in, and without going through all the details of the substitutions, I could rewrite cos 2x as 2 cos squared x minus 1, or 1 minus 2 sine squared x. And again, I'll go through one of them just to show you how easy it is to derive this. Sine squared x, cos squared x minus sine squared x. So I can use this identity here to say that, say for example, sine squared x is 1 minus cos squared x. And then substitute in here for sine squared x. So this is cos squared x minus 1 minus cos squared x. And then I distribute the negative sign. That's cos squared x minus 1 plus cos squared x. So 2 cos squared x minus 1. The reason why we like these two varieties of the cosine double angle formula is because they give us a solution in terms of only one function. Instead of having to use two functions, cos squared, cosine and sine, I'm able to get it down to terms of just either sine or cosine, depending on what is more convenient at the time. Sometimes it doesn't matter. Sometimes there is no convenience factor, in which case I might just stick with the basic identity. But again, most people I know do not memorize all three of these. They just remember how to find them if they need them. Some people memorize it. Some people are memorizing people. They love memorizing formulas. It's the way they learn. And if that's the way you learn, that's fantastic. Then do it. But those are our cosine double angle formulas. Tangent double angle, the same basic idea. Tangent 2x is the tangent of x plus x. Remember, the tangent alpha plus beta formula is up here. Just as a reminder, that's tan alpha plus tan beta, over 1 minus tan alpha tan beta. So if both alpha and beta are both x, that's tan x plus tan x over 1 minus tan x, or 2 tan x over 1 minus tan squared x. Now, double angle formulas in and of themselves are interesting, and we can play with them, and we can do identities with them and do little proofs with them. That's what they're good for the most part. They're shortcuts. But they don't give us new angles very easily because, let's face it, anytime I double an identity angle, I get another identity angle. Think about that for a second. What's my smallest identity angle other than 0? 30 degrees, right? If I double 30, what do I get? 60. My next one up is 45. If I double 45, I get 90. It's still an identity. If I double 60, I get 120. If I double 90, I get 180. So no matter where I go up the scale, anytime I double an angle, I get another identity angle. What it does do, however, it gives us sometimes different representations for those angles. So we might see the same value represented with different numbers. You're saying, what do you mean by that? Well, let's take a look. If we're working with identity angles, I might say, okay, let's find, using double angle formula, find the sine of 120. Using double angle. So instead of just using identity values, let's use a double angle to find that. Well, sine of 120, that's a sine of 2 times 60. So my double angle formula is 2 sine x cos x. We would call back to our double angle formula for sine, 2 sine x cos x, or 2 sine 60 cos 60. So that'd be 2 times the sine of 60. What's the sine of 60? Just as a good review. Get our brains going on this again. Sine of 60 is come on. Sine of 60. Root 3 over 2. Cosine of 60. 1/2. Actually, this works out really nicely. 2 times 1/2 cancels out. Root 3 over 2. Very exciting, isn't it? So double angle with identities, identity angles, not very informative. Doesn't do a lot for us. Except it does allow us to use just first quadrant angle to help figure out a second quadrant angle if we're having difficulty with that. I suppose that could be useful to us. What's more useful is, again, we go back into the alpha beta situation. If sine x is 5/13 and x is between pi over 2 and pi, find the cosine of 2x. Okay, sine x equals 5/13, so we need cosine 2x. Now, here's where knowing the multiple cosine formulas helps me. Cosine of 2x equals either cos squared x minus sine squared x, or 2 cos squared x minus 1, or 1 minus 2 sine squared x. Which value do I know? I actually know what the sine of x is, don't I? I actually know that value. So the formula I'm going to pick is this one, because I don't need to go through and draw my picture and calculate cosine or anything like that. I could use any of these formulas, but this one, I already know the value of sine x. I don't have to do any additional calculations. I don't have to draw a picture and find cosine. So that's going to be 1 minus 2 times the sine of x squared, which is 5/13 squared. Remember, sine squared of x means sine of x quantity squared. some people forget that sometimes, but sine squared x means sine of x, whole thing, squared. That's just the way we write it. So that's 1 minus 2 times 25 over 169. So that's 1 minus 50 over 169. So that's 119 over 169. Because it would be 169 over 169 minus 50 over 169. So there we are. Tangent beta is 15/8, and beta is between 180 and 270. Find the sine of 2 beta. For this one, we will actually need to... my blue is blue again. That's interesting. New computer. Must not have saved those settings. My blue's been purple for like the last year. Kind of disappointed that it's blue again. All right. So again, once again, and this is the other thing that people forgot, negative signs in quadrants. This is always a bugaboo for everyone. Tangent is 15/8. Opposite, adjacent, those are both negative, 17. So sine of beta is negative 15/17. Cosine of beta is negative 8/17. There we go. Again, dropping one of those negative signs, people would draw the picture perfectly accurately, but write this as positive 8. You really got to watch those signs. That was an issue. And sine 2 beta is 2 sine beta cos beta. So that's 2 times the sine of beta times the cosine of beta. So that'd be negative 30 times negative 8 is going to be positive. 30 times 8, 3 times 8 is 24, so 240 over 17 times 17 is 289. And again, your multiplication skills are kind of on the spot here. You need to be able to multiply without the use of a calculator. So that's one of the skills that we're working on. So in a way, this is a really good section to come back after a 5-day break on, because it does kind of reboot the brain. We have to think we're just reviewing really what we did before. We aren't throwing a lot of new stuff in here. We're using exactly the same techniques. Nothing that's really earth-shattering here. But again, we have to go back. We have to remember our basic formulas. And honestly, that's one of the biggest things that we're going to be working on, is just going back and remembering from the first half of the chapter so you can apply to the second half of the chapter. Sine of alpha plus beta is sine alpha cos beta minus cos alpha, or plus cos alpha sine beta. Sine of alpha minus beta is sine alpha cos beta minus cos alpha sine beta. The cosine formulas: minus okay. And the subtraction one Those are the 6 formulas in the first half of the chapter. Those are our 6 formulas. So make sure that you refamiliarize yourself with those. A lot of you are looking like, oh, I thought I was done with those. I thought I was free. No, you're never free. Once you learn something, you're a slave to it forever. Sorry. Okay. So if you look at the homework, a lot of the homework tonight is very basic. Oh, there's my book. You probably want to see what the homework is. Let's see if I can find the homework. I wonder if it transferred my bookmarks. It looks like it may have. Whoops. There we go. Oh. Ooh. Different scroll bar. Here we go. Page 228. Yeah, most of this is basically working in the coordinate plane type stuff. 19 is the only proof. And for 19 now we're starting to get into having to use some manipulation that we haven't had to before. Rewriting cosine 2 beta as 1 minus tan squared beta over secant squared beta. It's going to require you use some Pythagorean identity. Sine squared theta plus cos squared theta equals 1. You're going to have to play with that. It's the only proof I've given you. I've just given you one. But play with it, see what you can come up with. The rest of them are all pretty straightforward. Okay? That's it. That's all. How do I stop the recording? Oh, I minimized it? Oh, there it did.